Great. Hello to everyone who watches in the recording. So today we're going to study the last big class of convex optimization problems. Semi-definite programming. So far you kind of saw this progression where we started with least squares, which wasn't even optimization in the sense that it didn't require solvers. We went to LP, QP, QCQP, classically constrained quadratic programs, SOCP, second order con programs. Now we are at what we call SDP, semi-definite programming. Okay. SDP. So SDP is going to be the last part. Again, this we call it SDP for semi-definite programming. Okay. Yeah, so this is the most general convex optimization that we are going to encounter. After that, what we are going to see would be mostly problems that are close to convex but not convex, or applications of the algorithms that we see here, or some other material. So in terms of classes of problems, we are close to the end. There are more general still classes of problems than SDP, but SDP is already at the point where not all solvers work with SDPs. Even the ones that work with SDPs are not always perfect. SOCP, the ones that we considered before, people think of it as being more mature, if you want. So it is the kind of problem that is more of a guarantee that you can solve it, whereas SDP is more of a problem where you you have to somehow rely on the problem not being too large, for example, for it to be solved. So this is already at the edge of our capabilities in some sense, but it is widely used. This is widely used. This is not a fringe technology. This is a mainstream technology. Everyone uses it. So, all right, let's understand what it is. Let's understand what it is. So the general form of this type of optimization looks, a little bit mysterious, like this, where you have a linear cost. Okay, linear cost. Okay. Now you have something like a constraint that looks like this. Those are positive semi-definite matrices. Positive semi-definite matrices. And here you have decision variables, x. Okay, so x is a decision variable. So linear cost is with respect to x. This constraint with positive semi-definite matrices is with respect to x. Equality constraints with respect to x. What does this constraint mean? The most interesting part here is this. What does this mean? Well, this means that this whole expression, let me now, this whole expression has to be negative semi-definite. That is how we read it. Okay. The whole expression has to be negative semi-definite. Whereas, for example, this reads as matrix F has to be positive semi-definite, and matrix G has to be positive semi-definite. Okay. So this is how you can work with it. All right. So we can call this this thing here a linear matrix inequality, or LMI. Okay. the concept of linear matrix inequalities is largely used in control theory. When we talk about optimization, I think semi-definite programming is a more typical term. So like this whole thing is called SDP, and that is a correct way to refer to this thing, SDP, okay? Semi-definite programming. But in control theory, what people like is to refer to constraints as LMI, linear matrix inequalities, And in control literature, this type of formulation will be referred to often as LMI, because you don't particularly care about the whole problem, you care about the fact that some of the constraints are LMIs. But the LMIs in control are solved as SDPs, of course, right? And in control, even before SDP solvers existed, there were tricks how to solve it using Riccati equations and other things. So somehow both of them have history. So when you see control literature, you would often see linear matrix inequalities. When you see optimization literature, you would often see SDP. And if you are going to, for example, Google information about tricks or approaches to formulating things as SDP, often enough, what you have to, Google is tricks and approaches to LMI, not SDP, because people understand. People care about the constraints themselves, not necessarily about the whole thing, and that leads to books being called something like LMI in control. Like just a data books on how to work with LMIs and so on, instead of talking about them as SDP. I'm sorry for massaging this point so much, but it's just important to keep in mind that the word LMI is keywords that you need to use when approaching this problem, even though you can, like this, we call it SDP. Like it would be incorrect to call this LMI because this is not an LMI. LMI is constrained. LMI is here, right? Whereas this whole thing is SDP. So just don't let it skew you. You have to Google LMIs, not SDPs, when you look for example, control-related information about those things. All right. This was confusing. It's going to be more confusing in a second. So first, just some simple things. Let's say we have two LMIs, right? So we have one SDP with two LMIs. One LMI here, one LMI here. Okay, let me color code it differently.
Sorry, Professor. Yes. I have one question.
Yeah, go ahead. Please.
Like you said in previous slide, G and F are the positive semi-definite. So we're just adding them, and this whole constraint equal to the negative semi-definite. How is it possible? This thing we need to search on Google, like LMI.
So how is this possible? Well, yeah, it's a good question. And to be honest, like looking at this, like this is a general picture. And just in a bit, I think we'll kind of have a better understanding. But if I when I look at this, what it tells me is that X would have to be negative here. That is just the simplest way to interpret what's going on here, right? So I would say G better be somehow in the span of those matrices. And when I mean span, here I don't even necessarily mean in the column space, but somehow I mean that this, what we call this, I'm going into deep water here, so I apologize. What we call like positive semi-definite cone, something like this. So a space of matrices which are positive semi-definite, okay? So it is a subset of all matrices, and it is kind of like a manifold, which is lower dimensional manifolds in the space of n by n matrices, right? So inside this manifold, those matrices should somehow be kind of form a basis where G should lie. This is like an idea. And why? Because you have to not only choose such X that some of those matrices will be negative semi-definite, but they also should offset this guy being positive semi-definite. So that's the point. So to make a very simple illustration, if for example, okay, do I think I will be able to make a simple illustration on the fly? Maybe like, let's say G is something like this, right? This is a positive semi-definite matrix. This is a positive semi-definite matrix. Then if F is something like, for example, this, then we can choose X to be equal to, let's say, -3, and we get negative semi-definite as a result, right? That makes sense. If on the other hand, it was something like this, I'm not sure. This should be positive semi-definite, sure, but let's just make it like this. Notice positive semi-definite implies symmetric. So if G was something like this, which, by the way, I don't compute eigenvalues in my head so far, so I don't know. I hope this is positive semi-definite, but unfortunately I cannot do it on the fly. If G is something like this, then this would not be sufficient for to make it negative semi-definite. Why? Because those off-diagonal terms. I mean, maybe it would be actually. Maybe it would be because you can choose -30, and maybe those ones won't do anything. So good question. Not sure. Not sure. Not sure. But since you are allowed to have semi-definite, one example that you can say is this. This would definitely not work. So this F would definitely not work, and you have to have a second one. If this is F, let's say F1, this won't work. So you would better have F2, which looks like this. So if this is F2, and if this is F1, and if this is G, this somehow makes sense. This somehow makes sense. So in this case, you can choose X to be minus, let's say, 30, X1, X2 to be equal to -30, and together they would be, this sum would be equal to a matrix -10, 1, 1, -10. And that hopefully is negative semi-definite. That is just from the top of my head. And in a minute, you will see that we don't usually think in terms of X here, but yeah, this is kind of like how I would interpret this this problem. By the way, maybe I just don't have good enough intuition. That is another thing that about those problems. Intuition is difficult to have here.
Okay, all right.
Okay, hope I answered a little bit at least. All right. So let's consider this this again. So we have two LMIs. One LMI here. One LMI here. In the previous formulation, we weren't allowed to have two LMIs. In the formulation, we only had one LMI, right? But those are equivalent to a single LMI. How? Well, very simple. You just write it like this. So G plus Fi times X, this term becomes the first LMI. And here on the diagonal, F plus Hi times X is equal to 0. This is the second LMI. So basically, you create a diagonal matrix with, you know, your original LMIs to be spaced on the diagonal. So, by the way, is this correct? Is this correct? Yeah, this is correct. This is correct. Yeah. Why is this correct? It was because this xi here is actually a scalar. That's why it is correct. wouldn't work if xi was like a vector or something, but since it is a scalar, all of this works. Okay. Of course, in practice, we don't do that. In practice, our solvers, the ones that work with SDPs, usually allow us to directly input numbers of LMIs. Here, I have a very big suspicion that those zeros here are not helping. I suspect that they are making it worse. I won't know. I don't know. That is someone who designs solvers and pre-solve solutions. They have to say. But yeah, I suspect that those zeros are not helping. All right, but in practice, we just do it this way. Okay, but yeah, so those two are equivalent, but we don't have to do the transformation ourselves. Okay. Now we get a little bit closer to real life. In real life, what we say is SDP is a program where the cost function includes SDP variables. It doesn't have to include only SDP variables. It just includes SDP variable, like among others. Here again, I simplified maybe a little bit, or maybe I should have put something else. But yeah, SDP variables, where X is a semi-definite matrix. Let's say negative definite. That's what I decided to call it. Could be, of course, positive definite, right? The only difference is that you put a minus sign here. And you're allowed to, yeah, by the way, here, I think this oversimplification was a little bit too much. What I should have written here is a some linear constraint here is allowed to be some negative semi-definite. And you allowed to have linear constraints on X. So here I would have said, I think it would be better to say AX less than or equal to B. Yes, that would be better. And this less than or equal to B will be in terms of SDP. So that would be better instead of what I've already written here. Okay. So it's sometimes easier to directly work with semi-definite variables. And this is often how they look. But again, this doesn't somehow capture the essence of how SDP programs look. Before QPs, SOCPs, we kind of captured the essence. Here we really don't. I don't think this illustrates. So when we actually see SDPs, then you would see what they look like. All right. Now we'll go to the programs, but before we go, let me say one last thing. You remember that SOCP can solve a QCQP problem, right? And QCQP can solve a QP or LP problem, right? QP can solve LP problem. So all of them are kind of like this nested structure. Well, SDP is the most at the most outer range. SDP can solve SOCP problem. So we'll justify this claim later, but for now, I'll just mention that if you have, let's say, least squares of LP here, you can have a bigger circle in that is QPs. You can have yet a bigger circle. This would be QCQP, SOCP, and finally, this would be SDP. All right. This is often how we envision it. So if this is like LP, right? QP include LP. QCQP include all of those, and SOCP include all of those, and SDP finally include everything that we saw previously. All right. So this is how often we see it. And so far we proved everything. Now if we can prove that, for example, SOCP is included in SDP, if we can prove that, then we prove that SDP can solve anything. Right. Of course, if we could separately try to prove, for example, that we could separately try to prove that this is true, right? So sorry, that this includes LPs. That would have been a piece of cake. Why? Because you just choose your matrices here in such a way that they become like a. What does it be? A piece of cake? So I'm not sure. Would it be? Yeah, it would be, right? Yeah, it would be. You choose instead of Fi, you choose AI, right? So this become if you want to prove that this can turn into the structure of this type, A times X less than or equal to B. Why doesn't it look right? So if we want to prove this, that this can be achieved with the structure, what we can do is we can say, okay, individual elements Fi become now elements of this A vector, right? So Fi is AI. Now, individual elements of, G now becomes a scalar here in B. So G becomes essentially B. I mean, you have to choose the sign correctly. So it'll be like minus G becomes B. You just choose a scalar here, right? And sort of F, you also choose scalars and they are like AI. So this is how you go from LMI to linear constraints. You just shrink them to scalar size. And that is essentially how you go from here to there. How do you go to QPs and etc.? I mean, we can show it, but we'll just prove this connection here, SOCP to SDP. And if we prove it, we can prove everything else by inference, because we already proved that SOCP is QCQP, and that QCQP is QP. So as long as we can prove that SDP is SOCP, we are good. Right. We'll do it later. Before we do that, let us see what kind of problems we can solve. All right. So let us consider the following problem. We want to minimize the largest eigenvalue of matrix A. Okay. What do you mean minimize the largest eigenvalue? That is a little bit bizarre. Here, what we're saying is this is somehow like not a complete problem. This is somehow like a skeleton of a problem. Because let's say unless you put some constraints on A, minimizing the largest eigenvalue would be just make it a zero matrix. So there has to be some other constraints on A. Let's say maybe the first element of A has to be equal to 1 or something. I don't know. We have to put some constraints on A, basically. Otherwise, this problem becomes trivial. It's just a solution of 0. But anyway, we minimize the largest eigenvalue of the matrix A. How do you write it as an optimization problem? Well, you can write it as an SDP this way. You say, well, minimize T such that A minus I times T is negative semi-definite, or A is less than I times T. So what does this formulation by the way means? The way you read this is if you have this like less than or equal sign in the middle, it doesn't make any sense to say A is more negative semi-definite than T minus I, because both of them can be positive semi-definite for all you know. So in fact, the way is better to read it is to say A minus Ti are negative semi-definite. A minus Ti is negative semi-definite. So you put everything on the left and you say everything on the left is negative semi-definite. Or you can, of course, say Ti minus A is positive semi-definite. Right. Now, this would minimize the largest eigenvalue, right? Okay. So what is the proof? So if lambda is eigenvalue of A, then by definition, we know that A times V equals to lambda V for some vector V, okay? So we can, this is what it means to be an eigenvalue. That there exists an eigenvector that is being scaled by this matrix by the value alpha. Okay. Now, this can be rewritten in this form, right? A minus IT times V equals to lambda minus T V. Yeah, where did this come from? Where did this come from? Well, what is T times I times V? Well, this is just T times V, right? Identity doesn't do anything here. So this whole thing is just T times V. Just T times V with a minus sign. Well, what is this thing here? Well, it's again T times V with a minus sign. So we just subtracted some T times V from both sides. So we didn't do anything. We added a variable, but it's we subtracted from the both sides. It can be 0, can be anything, can be negative, positive, doesn't matter. This still works. Okay, good. So we achieved this strange equality. A minus Ti times V is equal to lambda minus T times V. But that means that lambda minus T is eigenvalue of A minus Ti. Okay. So we found this new expression with a new eigenvalue. Previous one, A, had eigenvalue lambda. New A minus Ti has eigenvalue lambda minus T, which, by the way, is a neat trick. If you want to do some transformations, you can think of, like with eigenvalues, you can keep in mind that subtracting identity does this with eigenvalues. Okay. Thus, what we have is this guy, if we look here, is going to be negative semi-definite. So we are going to have here negative semi-definite matrix. Negative semi-definite matrix, right? A minus Ti is negative semi-definite. Therefore, this is going to be less than or equal to 0. Why? Well, if A minus Ti is negative semi-definite, it means all its eigenvalues are negative. That's what it means to be a negative semi-definite matrix. All your eigenvalues would be negative. Hence, this eigenvalue of this matrix is also negative. Therefore, lambda is less than or equal to T. Okay. And what we do, so here, and what we do here is we minimize T. So we minimize T, and lambda is less than T. So if we minimize T, of course, we minimize lambda as well, because lambda is less. So you see this chain of arguments leads us to the fact that we minimize the largest eigenvalue of A. Okay. Why the largest? Well, because we didn't say anything about which eigenvalue here it is. And, at least, it's going to be true for all of them. So, while T goes down, the largest eigenvalue will have to go down as well. The smallest eigenvalue can, move up or down, doesn't matter. But the largest eigenvalue would have to move down for sure. because it has most pressure to be less than or equal to t as t goes down. Right. As I said, this problem, if you just, it can, if A cannot have negative eigenvalues, the solution will be zero matrix. If A can have negative eigenvalues, it can just go into infinity. So, you have to be careful. You have to add additional constraints that prevent A from going to minus infinity or any other degenerate solution. But what I wanted to emphasize here is that it is because of this constraint, which allowed us to consider this matrix as negative semi-definite, which in turn allowed us to reason about its eigenvalues being what they are, negative, right?
Negative.
It is because of this chain that we were able to reason about the largest eigenvalue here. It wouldn't be impossible without this semi-definiteness. So you can see the role it plays. It allows us to go, into those strange regions where previously it would have been hard for us to go. Like, what is the largest eigenvalue, etc. It's not easy to reason about. But now with semi-definiteness, we suddenly can. So that is like first example of the usefulness. Do you have questions? Right. Well, then I will move on. The next one I think would be maybe more familiar. So in control theory, you remember we have Lyapunov equation, something called Lyapunov equation. Right. And that is a condition whether or not autonomous LTI in the form x dot equals to ax is stable. So if this autonomous LTI is stable, for this autonomous LTI to be stable, you can, to check it, you can use the Lyapunov equation. If you can find such P, which is positive semi-definite, and you can find, and its derivative, I'm trying to derive it on the fly. Let's not. If you can find such P that's positive semi-definite, and for it Lyapunov equation holds, then the system is stable. How did we get the Lyapunov equation? Well, we got a Lyapunov function, which looks something like v of x is equal to x e x, and has to be positive everywhere except at 0. And the derivative of this function has to be negative everywhere except at 0 for asymptotic stability. And what do you mean by derivative? The derivative with respect to time is taken with respect to this variable, which provides us a vector field, as we call it, because x, like, when you take derivative with respect to time, you would get x dot times p times x plus x times p times x dot. Where do you get this x dot? From some vector field, right? From something that actually has this dynamic of changing with time. And this is provided by this autonomous system. So you substitute it, and you get essentially Lyapunov equation. Since you want it to be everywhere negative, you have this condition here, that this, what you get here in this form with x's will be x transpose times a transpose p plus p transpose a times x, all of this in brackets, and that has to be less than or equal to 0. But less than or equal to 0 is good, but if it is equal to 0 somewhere except at the origin, that is not asymptotic stability, that is marginal stability. So what we want is asymptotic stability, so we require it to be, and by the way, don't quote me on that. We need to double check those statements each time we make. What we need to check is that minus q, so we add minus q here. In real practice, the reason we add minus q here is not really because we care about marginal or asymptotic stability. It is because if you don't add minus q here, the solution will be 0. Just put 0 here, 0 here, 0 here. And if you have 0 here, that's the solution. So your solver will always give you zeros. So you have to somehow ask it, please don't give me zeros, give me something better. And it will give you something better if you put a minus q here. So that is the story. Lyapunov equation, right? If such P exists, then the system is stable. How do you check it as SDP? Well, very simple. You say minimize subject to P, minimize 0 with respect to P, such that P is positive, and AP plus PA plus Q is negative. That's it. That's it. That is the whole situation with Lyapunov equation as an SDP. See how simple it is. Of course, it was simple before you could just call some MATLAB function probably to solve your Lyapunov equation, LYAP or something like this, probably provided you with a solution to Lyapunov equation. But as an SDP, it is very elegant. So you have this single SDP with 2 LMI constraints, this one and this one. So single SDP with 2 LMI constraints. Okay. All right. And this is how you check stability with an LMI. Of course, if this was all it was good for, probably it wouldn't be as popular in control. But that is just a taste of what it's good for. It has much more to offer. Before we go on, let me show you how this is coded. So, for example, we have, let's say, a random system with a dimension 7 by 7. Notice the way I generate random systems here. Random systems are useful. You have to try to understand how they work in order to use them. But they're very useful in testing your optimization programs. So let's say this is a random system. Here is a random Gaussian distribution matrix, random. This n means Gaussian distribution. Minus, this is a random number, again Gaussian. Sorry, not Gaussian. This is now from uniform distribution. See, because no n here. So it is uniform distribution between 0 and 1. Times I, identity matrix. Since we multiply it by -3, it can dominate over Gaussian, which kind of declines at around 1. So it will be dominating in the unit circle, but it's not going to dominate over, like, it's the height. How should I put it? You can expect numbers such as 1 to appear in this matrix, but you don't expect like 10 or 20 to appear. They can, but you just shouldn't expect them. So this -3 identity will dominate over this matrix in most cases, not in all cases, in most cases, right? And this randomness here would make sure that sometimes this coefficient would be so small that this matrix will dominate. So this is how I construct matrices which are mostly stable, but sometimes unstable. Okay, that's definitely not something you need to copy from me. It's just like one way to do it. Right. So this is how we do a CVX in MATLAB. In Python, it will be similar. Just like this call, you won't have to make it, etc. But very similar. So you say begin CVX. You denote a variable p, which is symmetric. In Python, you also declare it symmetric. You just declare it in brackets. You declare your cost function. The cost function is minimize 0. Minimize 0 in this case, because we don't have any other cost, right? So minimize 0. Now, our constraints are p bigger than 0, AP plus PA plus Q less than 0. Notice that those constraints are interpreted as LMIs only because of this statement here. If it wasn't for this statement, those constraints would have been interpreted as element-wise inequalities. So unless you provide those statements, the CVX would think that you are trying to do element-wise inequalities. It won't throw an error, and that is quite dangerous. So you have to double check that CVX actually respects your constraints. Okay. How do you check that it respects your constraints? How do you check if you didn't make a mistake? Well, after you solve the problem, so it has status solved, you can print eigenvalues of this matrix, and they have to be, for this matrix, strictly negative and real. For this matrix, strictly positive and real. So if you see complex part, or if you see incorrect sign, you know that you managed to mess somewhere. So easy to fix and easy to catch if you are going to print eigenvalues. Important part of working with LMIs is to distrust yourself and keep printing eigenvalues. At some point you feel like, oh, I know what I'm doing, I don't need to print eigenvalues. And that's when you start to make mistakes. So keep printing them. Not so difficult. Not so difficult. All right. If the problem is not solved, then printing those would cause an error because they would have not a number elements. And instead, you can just print this if you want. Printing this is nice because you know when the problem can or cannot be solved. If, by the way, can someone tell me in which case would algorithm go towards this branch? In which case would the algorithm go towards this branch? What should be the properties of matrix A for the algorithm to go towards this branch? Someone tell me, please.
If A is positive definite?
Positive definite, correct, but more general. That is a particular example when it will go into this branch. More particular, like, you know, can you give me more general answer? When will the algorithm go into the branch line 14? Well, the answer is when A is not Hurwitz. If A is Hurwitz, so the eigenvalues of A are strictly non-positive, then it will go into the branch 12. So it will find a solution and it will place it. If the eigenvalues are, at least one eigenvalue is positive, has positive real part, there will be no solution to this equation and it will go to the branch 14. So branch 14 is not actually like error catching branch. So it's not like accept, try, etc. Right? Try, accept. It is not this like situation where you want to see what kind of mistakes you made. No, it's like as long as the system is not stable, you're going to branch 14. If it's stable, you're going to go to branch 12. Because failure to solve this problem implies instability of the system. That is the idea of Lyapunov stability criteria. Okay, it is if and only if condition for linear systems, of course, right? For this class of autonomous linear systems. All right. Okay.
I have a question.
Yeah, go ahead.
So for checking criteria, this is working only for this example, Or we can use this in any like SDP example, like checking the eigenvalues. Print this.
You're talking about the code?
Yes, yes.
Yeah, of course. In eigenvalues, you remember the difference was that here. Let me try to somehow illustrate. Apologies. Oops. Like this. So in the example with eigenvalues, what happened was we would have t here, right? Minimize t, remember? Right? We wouldn't have these conditions here. Instead, what we would have is one condition which says a less than or equal to ti, where I would be, let's say, I am. And I think that's it. That's it. Of course, this again would be and the variables here would be, variables here would be instead of p, would be I, would be a, and you would have additional variable t, which is not symmetric. T is, I mean, it is scalar, so it does make any sense. It should be symmetric, of course. So, I mean, all scalars are symmetric. So this is how you can solve the eigenvalue problem, unless I written something correctly. But this is going to probably produce you a minus infinity results, something like this. So you better have some other restrictions on what values A can have. What values A can have. If A is positive semi-definite, for example, if A is additionally positive semi-definite, then the solution will probably be 0. I think. If A is, I don't know if this is legal here. I don't trust my intuition with SDPs. I think this is legal. So if this is the case, I think we'll probably A would probably have the same. The A would have then some kind of eigenvalue, and I'm not sure, but I think it might be the same as Q, but that I'm not sure. So don't quote me on that. I'm not sure what kind of eigenvalues A would achieve, but that I think would make problem at least bounded. Anyway, the code would definitely work for any SDP. It is just that SVX has more tricks than that. So this is just a very simple example of a code. More questions? All right. Now let me. Now remember we had also discrete Lyapunov equation for discrete systems. Discrete Lyapunov equation looks something like this: x sub I plus 1 equals for a system discrete LTI autonomous system, which is x sub I plus 1 equals to a times x sub I. For this system, you have to find such p, such positive semi-definite p, that a times p times a minus p plus q less than or equal to 1. The derivation is, remember, the Lyapunov function of the next step should be less than or equal to the Lyapunov function of the current step. And the Lyapunov function of the next step would be dependent on x sub I plus 1, which after you open it up gives you a on both sides. That's how you get this. And this is the previous step. And q, we have it from the same source as before. We could have had a 0 here, but that would make a zero solution always acceptable. So we put q here. to avoid zero solutions. So this is the Lyapunov criteria, discrete Lyapunov criteria. Okay. What do we do? Well, we can represent it as SDP. Again, we have here our decision variable P. P is bigger than 0. APA minus P plus Q less than equal to 0. Those are two LMIs that we have. Okay. Two LMIs. That's it. Very simple. And the code for this problem, you can already kind of imagine how it looks. Same here. The difference here, notice I say 0.35 times randen. Randen is, remember, Gaussian distribution. And n. Why 0.35? Well, because now I want A to be sometimes sure, sometimes not sure. What is sure? Sure is a matrix whose eigenvalues are less than or equal to 1 by absolute value. So for discrete control systems, to be stable, the state matrix has to have eigenvalues by absolute value less than or equal to 1. Those matrices are called sure matrices. Terrible idea, but let me try to spell it. Sure, I think that's how it's spelled. So, same as previous was Hurwitz, this is sure. Okay. The rest of the code, so if we just leave it along as the Gaussian distribution, apparently for a system with a 7 by 7, the eigenvalues are not going to be very often sure. So I wanted to make it small, to make it more often to be sure. All right. Now the rest is the same, exactly the same. So variable declaration, positive definiteness on the variable constraint. We do exactly the same here, allowing us two branches, solved, not solved. Everything is extremely simple. So, like, same as before. Questions? All right. So now we can also design an LMI for the system of this form, AX plus BU. And this LMI here would determine if the system can be stabilized. So remember, there is this idea of controllability. So this LMI, you can think of it as a controllability criterion. Or you can think of it as a control design. Why? Well, because if we choose control U equals to KX, notice not minus KX, KX. And the control law, the K would be chosen as L times P inverse. Then this would provide a stabilizing control. So this system here, would be stabilized by this control law with this K matrix, where P and L are solutions of the equation that we see above. So L comes from here, P comes from here. Okay. So this can be done this way. How did we get it? Well, we're actually going to have next, on this Thursday, we're going to have a whole lecture just on how to deal with this type of problems. We're going to go deeper than just this formulation. We're going to go, into much more detail. So for now, I will just, I'm not going to give you a derivation. It's going to be next Thursday. But, Now, for now, you can just kind of see that this guy, we can solve controllability and design control at the same time. You can think of it as LQR analog, right? LQR also allowed you to get K, and if you got K, that means the system was controllable. So this somehow is a little bit of a cheat, saying that it is a controllability criterion, because it's just control design method. And then if you design the control successfully, it means the system was controllable. All right, so this is the what you can use to design control for your LMI, or sorry, for your LTI system. Right. Let me show you in code. Again, derivation on Thursday, but now let's show it in code. So we have random A, B. We declare two variables, P and L. Only P is symmetric. L doesn't have to be symmetric. It somehow makes sense because L would have to be M by N, right? It multiplies B on the left. So, and it has to have the same dimension as Q and A and P. So N by on the right. So M by N, right? So it cannot be symmetric because it's not even square. And you get the familiar LMI here, but with just longer instead. And this smaller LMI condition here. Now, to convert P to numbers from CVX variables, you do this. Full means you convert into numbers. Then you can compute K as inverse of L times P of P. And then you can print eigenvalues of A plus BK, and remember, because control law was U equal to KX, not minus KX. So there's a plus here. All right. So this is what we can do with SDP. This is what we can do with SDP for control design. Right. We'll see more of it on Thursday. Okay. Do you have questions? Right. Yeah. So this is it for Lyapunov part. So I will just quickly run through it. So what we did so far was just see Lyapunov stability criteria for the continuous time, discrete time, and even control design for continuous time systems. Okay, that's what we did, and the code is kind of the same each time. And before that, we did eigenvalues. How much time do we have? We have about 20 minutes, I would say. Right,
Yeah, we have about 20 minutes.
Yeah, not enough for sure. Like halfway through only. So sad. All right, maybe we'll see. I'm not going to rush it. It's a very important part of the course. So, right. Now, another application of LMIs, SDPs, is work with ellipsoids. So eigenvalues we already saw. Some control ideas we already saw. Now, maybe the most important part, not what's the most important, but one of those key parts is working with ellipsoids. You would think, why ellipsoids out of all things? I mean, ellipsoids very important. Geometrically important in control, so important. Right. So what about the ellipsoids? Well, let us begin by thinking about how we can describe unit sphere. So unit sphere is all x such that x is by norm is less than or equal to 1. Here we mean the second norm, so Euclidean. Okay. Good. Now, an ellipsoid can be seen as a linear transformation of a unit sphere. What do we mean by that? Well, we take a unit sphere, we multiply it by matrix A, shift it to by vector B, and matrix, remember, is a stretching, rotation, stretching in general. So here's unit sphere. And let me just draw it, I guess, in some better colors. Here's unit sphere. And here is a unit sphere multiplied by ellipsoid, I said by a matrix, and shifted. So we shift its center, right? We shifted its center, and we stretched it. Okay, we stretched it. Where does this rotation, stretching, and rotation comes from? It comes from SVD. Remember, any matrix M is equal to U times sigma times V transposed, where those two matrices, let me show them, are rotation matrices, and this is a diagonal matrix. So it rotates, stretches, then rotates again. Okay. What do you mean? What exactly is being rotated there? Well, vectors are. So a vector is being rotated, then stretched, then again rotated. What is this unit ball? It's a collection of vectors. So those vectors will be first rotated. That does absolutely nothing to the unit ball. They just change orientation. Then it's stretched, so it becomes an ellipsoid. Stretched ball is an ellipsoid. That's what what ellipsoid is. And then this ellipsoid is going to be rotated again. Second rotation again, you can say it does nothing, but arguable. Right? So that is what it is. And A here would have to be a semi-definite matrix. In fact, positive semi-definite matrix. This is important. So it is a positive semi-definite matrix. Being a positive semi-definite matrix, you can imagine it having the eigendecomposition, which plays a role in what ellipsoid is. Eigendecomposition often is an important part of what makes an ellipsoid. But yeah, so this will be a positive definite matrix. All right, good. Now, in order to represent ellipsoids better, we can change this A equals to B. So remember, this is what we're working with here. We can decide to change it to call it Z. Okay, we can call it Z. So we would have variable Z on the left-hand side. But what about X? Well, X becomes this variable X. It becomes Z minus B. Okay, so like this B has to go somewhere. It goes to Z. So Z minus B multiplied by A inverse. That is the first time when positive semi-definiteness plays a role. Since it is positive semi-definite, let's say positive definite, it is invertible. So we can do this trick. If it was not invertible, not full rank, we couldn't do this trick here. But we can because this is positive definite. All right. So we get the expression for what X is. X is this guy. Now that we saw this, we can describe our ellipsoid in this fashion. We can describe it as being equal to Z, all Z, such that norm of B times Z plus C is less than or equal to 1. Well, what is this B and what is this C? Well, B is actually just A inverse. So this guy that stands in front of Z, that is B, right? Because what we are supposed to have here is X less than or equal to 1, right? But we don't have an X anymore. We have to have expression for T, but we can rewrite it to say B is equal to A inverse. Okay. And what is C? Well, C is minus A inverse B. So it is kind of like this guy multiplied by this guy. So that's it. We have to have X less than or equal to 1. Instead, we have BZ plus C less than or equal to 1. But that is the same thing. We just changed variables. So what happened here is that we, in new variables, we have ellipsoid to be equal to all Z, such that some linear function by norm is less than or equal to 1. Okay. So now let's look at two representations. First representation, AX plus B, X by norm less than 1. Second representation, all Z, such that BZ plus C less or equal to 1. So this linear function shifts, either it is here or it is here. It should be somewhere, but in one of those two places. Okay. Now, let us consider ellipsoid of the form AX plus B, X less than or equal to 1. For this ellipsoid to be bigger, the A have to be bigger in a sense. So have like larger eigenvalues, for example. Okay. So for this ellipsoid to be bigger, A has to be bigger. All right. In order to clarify what we mean by bigness, instead of saying like large eigenvalues, etc., we can talk about determinant of A. And you remember determinant of A has something to do with eigenvalues too, right? Okay, so we have to talk about determinant of A. So maximizing the volume of ellipsoid is linked to maximizing determinant of A. Okay. But this is the same as minimizing determinant of A inverse. Why? Well, determinant of A inverse is 1 over determinant of A. So the smaller this guy is, let me now use my highlights. The smaller this guy is, the bigger this guy is. That is why maximizing determinant of A is the same as minimizing determinant of A inverse. Okay. Why is this craziness is going on here? Like, why do we talk about all those things? Well, in practice, we will want to work with biggest ellipsoids or smallest ellipsoids, right? So we want to know how to do it. Determinant happened to be one of those functions that we can actually use in convex optimization. Same as norm, same as squares, same as linear functions. Determinant happened to be one of those. And we usually only use it as it's the cost functions, but we can do it. So it's important to know what we can do. And but there are like various restrictions, so we have to be careful with what we're doing. But the determinant of A inverse is just be sure is determinant of B. Okay. You remember B is A inverse. So maximizing determinant of A is the same as minimizing determinant of B. Okay. Same results. Right. Confusing. Now, let us look at one more slide. Ellipsoid in the form that we saw before. Okay. This guy, for this, the logic is reversed. It will be bigger if B is smaller. Why? Well, if B is bigger, that leaves kind of like less room for Z to be anything. If B is a very huge matrix, even a tiny variation of Z would already break this condition. So B should be as small as possible. If B is equal to close to 0, almost any Z would satisfy this condition. So it would be a huge ellipsoid. Since ellipsoids are all Z which are satisfying this condition. Okay. Now, we want to minimize, so to maximize the volume of this ellipsoid, we want to minimize the determinant of B, which is the same as maximizing the determinant of B inverse. And you notice this, we already saw it before. Minimizing the determinant of B, yeah, that's what we saw on the previous slide. And the determinant of B inverse is the determinant of A. And maximizing the determinant of A is again what we saw on the previous slide. So indeed, it makes perfect sense in both cases. So geometrically, it makes sense. B and A are related as inverses. And indeed, we can reason about it through those determinant relations between inverses. Or through the just generally looking at the, like this tells us that we should minimize determinant of B or maximize determinant of A, right? Just looking at the equations. And the relations between them also tells us, like this equation also tells us the same story. So sanity check, we arrive at the same result in two different roads. Good. Good. Now, let's consider the first practical application of all of this random knowledge that I brought you. That's actually extremely useful, is, you know, at least quite useful, let's say. So given a V polytope defined by its vertices, Vi, find a minimum volume ellipsoid E epsilon containing this polytope. So we have a polytope V given by its vertices. We want to find the minimum volume ellipsoid that contains the polytope. So graphically speaking, graphically this would look something like this. Here's the polytope, and I'm trying to find the smallest possible ellipsoid that would contain the polytope. So let me just try. So this is clearly not the smallest possible one, right? Just some ellipsoid that contains it. And for example, maybe, I don't know, we'll manage, I'll try. Maybe something like this is closer. Yeah, so the blue one is just contains the polytope, but the green one contains it and is the smallest possible volume ellipsoid that contains it. So this is what we're trying to do. Okay. All right. So let us define the ellipsoid in this form. Epsilon equals to all z, such as bz plus c, by norm is less than or equal to 1. So this ellipsoid will be smaller. We want to find the smallest volume ellipsoid. So the smaller when b is bigger. Determinant of b is bigger, not the norm determinant. Determinant of b is bigger. So we want to maximize the determinant of b, which is the same as minimizing the determinant of minus b inverse, so a, right? But we don't have a here, so we'll stick to b. So we want to minimize the determinant of -1. There is a trick in optimization that allows us to work with determinants, and that trick is that instead of minimizing the determinant itself, we can minimize the logarithm of a determinant. And somehow logarithm of a determinant is the convex function that we can minimize. So in fact, in CVX, it is implemented as log_det, and it minimizes the logarithm of the determinant of an inverse. Okay, because inverse is not convex function by itself. Determinant is a crazy function. Logarithm is also a little bit crazy, but logarithm of a determinant of an inverse is a convex function. So That is like that is the interesting world in which we live, right? Okay. Now we want B to be positive definite because B is here, and we all want B to be positive definite. Otherwise, we would have something nonsensical. We want B to be invertible. Its inverse is, remember, A, also positive definite matrix. So now we can write a condition that this polytope is inside this ellipsoid, and the condition would look like this. The condition would look like this. Where did this condition come from? Well, we know that, let me clear this. We know that this condition is for Z, for the point Z, to be inside the ellipsoid. Okay. And what is the condition? Well, BZ plus C is less than or equal to 1. That is the condition. Well, if we substitute V into this condition here instead of Z, it should also work because V is supposed to be inside this ellipsoid. So the ellipsoid is all Z, for which the condition works. Well, it should work for V as well, right? Well, this is how we get this condition. And with this condition, we obtain the, what we call it, Lerner-John ellipsoid. Lerner-John ellipsoid. And here you can see the formulation. So the optimization program itself is rather simple. We have two decision variables. One decision variable is B. Another decision variable is C. Because, so notice V are constants. The edges of the ellipsoid are constants. But B and C are decision variables. The cost function is, you can think of it as a combination of all of this as a cost function. So log that of inverse is like one cost function, and that happens to be convex. We have a requirement here, B is positive. And we have another requirement here that this thing is negative. This thing is negative. Of course, this is not clear if this last requirement looks like, if it is LMI or not, right? If it is SDP or not. So let's investigate it a little bit. Or are we going to investigate it? Don't see a slide for that. Very interesting. No investigation needed. Yeah. What else? Is right, I'm not going to improvise here, but hopefully we will see the form in the code. All right. You should be suspicious when you see SDP under the norm. The next logical step would be to square the norm and work from there. Right. But I'm going to leave it here and don't want to improvise during this lecture, and we don't have time for improvisation size. Let me see. Do we even have time for? Yeah, we don't have time. So let me just quickly. We have time to quickly run through it. Right. If you allow me, I will just quickly run 5 minutes and I will be done. Right. Another that was how you find the smallest ellipsoid with inscribed polytope inside. Now we can find the biggest ellipsoid, biggest ellipsoid, with the what do you call it? Biggest ellipsoid inscribed inside a polytope. So let's say you have a polytope, and you want to have an ellipsoid inside it. Say this is an ellipsoid, and you want to try to find the biggest one that would fit inside. So you can increase, and you want to find the biggest one that would fit inside. That is the problem of the biggest possible inscribed ellipsoid. Okay. So this problem can be is considered through H polytope. Previous one's V polytope. This time the polytope is H polytope. So this is defined by half spaces. Half spaces, you remember, cut off like half of the space here, half of the space here, half of the space here, half of the space here. Right. So we want to find maximum volume ellipsoid. For this, we'll use this representation. Where epsilon is equal to Cx plus D, where x is less than or equal to 1. So this second representation, right? Well, this ellipsoid will be bigger when determinant of C is bigger. Thus, we can write the minimization as minimizing determinant of C inverse. Okay, minimizing determinant of C inverse. All right. Let's minimize determinant of C inverse. So now we know that all of those points, let me show them. All of those points should lie inside the polytope, which implies put my controls all the way. So let's say, which implies that they have to satisfy these conditions. We put this Cx plus D inside this condition Ax less than or equal to B, and we get the following. This is the same linear inequality, but this time with the all points of the ellipsoid being required to satisfy it. So this should hold for x norm less than 1. So the worst case scenario, remember that we saw it before when we talked about Chebyshev polytope. The worst case scenario here is when this guy aligns perfectly with this guy. That is when the whole thing becomes as big as possible. When X aligns perfectly with A and C. That why is this worst case scenario? Well, you can reason about it through just finding a derivative, or you can say X, orientation of X can be anything. Length of X is fixed. So this dot product is of two vectors with fixed norms, but the angle can change. Optimal solution is when the angle is equal to 0, cosine is equal to 1. So that is why the worst case scenario is when X is aligned with A times C. So X should be aligned with A times C, but the norm of this whole thing should be equal to 1. So we divide it by A times C. Now we get this expression here for X. And we put this expression back into here. So what happens is we have A times C times A plus A times D. So this part is just A times D, right? Remains the same. But when we put, let me, I guess, erase all of this possible. When we put this guy here, what we have is one instance of A times C here. One instance here. We have another instance of A times C here. Here. They multiplied, so it is A times C squared. A times C squared, which is the same as A times C norm squared, because the square of a vector is like a norm squared. So dot product of vectors itself is a norm squared. And we divide it by norm. So the square goes away, and what we have is just A times C norm. All right. All of it is less than or equal to B. Less than or equal to B. Right. Okay. Okay, so this is how we get to this expression here from those two expressions, from this and from this. So from definition of an ellipsoid and definition of polytope, we get this expression. And this expression allows us to, again, solve the problem for the maximum ellipsoid. Again, notice that the matrix is under the norm. All right. So in both cases, we managed to arrive at around kind of a similar thing. Here, the matrix less than equal to 0. Here, the matrix less than equal to 0. And this is the solution. This is the resulting problem. This is the resulting problem. Right. In both cases, we use the same cost function. Right. That is it. We don't have more time today, so we don't have more time today. So we'll have to leave something for the next class, and that is namely how to convert SDP to SOCP. Okay. And next time we'll concentrate on derivations of this type of programs, and general LMI and control. Apologize for taking so long. Do you have any questions? Right. Then we'll see each other in 2 days. See you then. Bye-bye.
Thank you,
Okay,
Professor.
goodbye.
Bye.
Thank you.